This video will take you from ancient Greece, the birthplace of electricity, to the birthplace of series and parallel AC circuits, better known as Wollongong. A circuit is any combination of elements that will result in a continuous flow of charge or current through the configuration. In an AC circuit, the flow of charge changes in both magnitude and direction with time. In this video, the elements that make up our circuits are resistors, capacitors, and inductors, which all have an associated impedance. Impedance tells us how much the element will impede the flow of charge through a circuit. It is measured in ohms. The following formulas can be used to find the impedance of these three elements. They are shown in both polar and rectangular forms, and there is also the breakdown of the inductive and capacitive reactances. These impedances are represented by an impedance diagram, which is shown at the bottom right of the screen. The axis that each impedance lies on corresponds to the angle of the impedance in polar form. The inverse of impedance is admittance, which is a measure of an AC circuit's ability to allow current to flow. Now that we know all that, we can look at series and parallel AC circuits. Two elements, branches, or circuits are in series if they are connected at only one common point or connected sequentially. Series connected impedances can be simplified to an equivalent impedance using the first formula. Two elements, branches, or circuits are in parallel if they share two common connections or nodes. Impedances connected in parallel can be simplified to an equivalent impedance using the second formula. The angle associated with the total impedance is the angle by which the voltage leads the current and is represented by a theta subscript t. The behaviour of an RLC circuit will depend on the frequency response of the individual components. The graphs below show how each element varies with frequency, and it really is just a graphical representation of the equations I wrote for you 2 slides ago. As you can see from the graphs, inductive elements favour higher frequencies, whilst capacitive elements favour lower frequencies. So the frequency can determine whether the circuit will be more inductive, capacitive, or vice versa. These two elements might even cancel out, leaving a purely resistive circuit. This happens when the angles associated with both the inductive and capacitive reactances are equal. Now, when it comes to solving series and parallel AC circuits, you can almost take the same approach as DC circuits. They can be solved through applications of Ohm's law, voltage and current divider rules, and Kirchhoff's laws. The only big difference being you are dealing with quantities that have a magnitude and a direction. It can be useful to simplify the circuits by making block impedances, and drawing the circuit always helps. Now here is a summary page that you can screenshot and use for study if you found this video useful. In conclusion, I would just like to point out that we started in ancient Greece and now we're here. I'm Daniel Zanata, thank you for watching.